A titration is a common laboratory procedure where we gradually add one reactant to another reactant. And the typical setup looks something like this. You have one reactant in you dispense with what's called a burette. Okay, so you add it drop-wise into the other reactant, which would be put in what's called a flask. Okay, the reactant in the burette, the reactant that you add gradually, is called the titrant. Now, the goal of a titration is to find the equivalence point. At the equivalence point, the mole-to-mole ratio of the reactants that have been mixed would be equal to the ratio of their coefficients in the balanced equation. We typically design a titration so that we want, since we're looking for the equivalence point, we want something dramatic to occur, a dramatic change to occur as close to the equivalence point as possible. We can't get it really exactly at the equivalence point, but we design our titration experiment so that something happens dramatically as close as possible to the equivalence point. So that point in the titration is what we would call the endpoint. So endpoint is a titration is generally designed so that the endpoint is as good an approximation as possible for the equivalence point. For practical purposes, we say at the endpoint we are at the equivalence point. Now, the goal of a titration is to determine an unknown amount or concentration of one reactant. So that unknown reactant is called the analyte. And you base that on the known amount of the other reactant that would be involved to reach the equivalence point. So the known reactant, the reactant that you know, would be called your standard. Let's look at an example here. In the titration of acids, you want to determine an unknown amount of acid in a flask, and typically what you use is sodium hydroxide as your standard. And so in a typical setup, you would put your sodium hydroxide here, your standard here in your burette, so it will be your titrant. And your acid would be down here. And you add something called phenolphthalein, a couple of drops of that to the acid in the flask. And what will happen is once you reach the end point, that phenolphthalein color changes drastically, almost instantaneously. Just one little tiny drop would cause when you're at the end point, would cause the color of the solution to change from colorless to pink. So let's look at an example here of data you might get from a titration of as an acid by sodium hydroxide. Suppose you have a 0.4981 molar, that should be molar, standard solution of sodium hydroxide, and you use it to determine the amount of HCl in a sample. How many moles of HCl are in your sample if 15 mils of that solution, your standard solution, is required to reach the endpoint? Now, to be able to solve this problem, you have to know the reaction. HCl plus NaOH, acid plus base, gives you salt and water, right? The H plus from the acid and the hydroxide from the base gives you water, and the other product of your reaction would be the sodium chloride. Okay? And so this equation, as you can see, is already balanced, so that means you have a 1 mole to 1 mole ratio at the equivalence point. So you say at the equivalence point, the mole-to-mole ratio of HCl would be equal to the moles, to sodium hydroxide is 1:1. So moles HCl would be equal to the moles of sodium hydroxide that you've added when you get to the endpoint. So what information do we have here? We have 15 mils of your sodium hydroxide solution, which has a known molarity. So let's calculate that. Calculate moles sodium hydroxide. So you say moles sodium hydroxide added to reach the endpoint would be equal to molarity times volume. The molarity of the sodium hydroxide is known. Okay, so your sodium hydroxide is your standard. It's 0.4981 moles per liter. And the volume of your sodium hydroxide that was required to reach the endpoint was 15 mils. So you multiply that by 15.00 times 10 to the negative 3 liters. Okay, that's milliliters right there. So this gives us 0.4981 times 15, 7.4715. Okay, I have 4 sig figs here, 4 sig figs here. Okay, let me check my sig figs. Yeah. So I should have 4 sig figs in my answer. 1, 2, 3, 4. I'm just going to keep that extra 5 there. So that's going to be, liter cancels out. So that's going to be moles of sodium hydroxide. So that means if that's what's required to reach the endpoint, that must be the moles of HCl, right? So moles of HCl is moles sodium hydroxide times 1 mole of HCl reacts with 1 mole of sodium hydroxide. So times 1 basically. So this will give you the same answer, 7.47. Oh, sorry, that should be 7.4715 times 10 to the negative 3 moles, right? I forgot this one right here. So that's really a millimoles. Okay, so 7.4715, so I can round this off now. 7.472 times 10 to the negative 3 moles of HCl. Okay.